Okay, so I think the recording has started. Okay, welcome everyone. So maybe let's start with a few administrative announcements. A quick reminder that we have the second tutorial tomorrow. So the schedule is already in the website. It's like from 10 to 11:30, but in the same link as the regular lectures. And for people who cannot attend the tutorial, like it will be recorded if you have any clash with other courses. Other than that, I think tonight 10 o'clock is the deadline for the first assignment. So I still see a lot of you haven't uploaded your solutions in Gradescope. Please make sure that you finish it on time, and assignment 2 has already started from Monday, and like the only missing piece for the assignment 2 is evaluation metrics, which is what we are going to discuss today. And you will also learn more about how to use scikit-learn and PyTorch in tomorrow's tutorial. But remember, assignment 2 still expects you to implement things by yourself, not use ready-made algorithms from scikit-learn. Okay, so let's begin. Let me share my screen. So 1 second. Okay. Okay, so let us begin. So just a quick recap of what we discussed in the previous lecture. So in the last couple of lectures, we focused more on probabilistic generative models, right? So we looked at a whole class of or family of algorithms, starting from GDA and its nonlinear version QDA, and you have the diagonal approximations for these, which becomes Gaussian naive Bayes and diagonal, diagonal GDA, right? And then we also looked at discrete version of naive Bayes algorithm if your data, the input X is discrete, right? So this is where we stop. So before we look at some other classification algorithms, like we are going to spend probably the next 5-10 minutes in discussing the evaluation metrics for classification. Okay, so remember that in the case of regression, the standard evaluation metric that we are using is RMSE, right? Like the root mean square error, which is in the same scale as the value that you're interested in predicting, and it's a good metric, right? Like, so now in the case of classification, so far we have seen only one metric, which is accuracy. Okay, so let's, like, for today's discussion, like I will just talk about 2 class problems, and you can extend these discussions to multi-class problems by yourself. Okay, so let's consider a 2-class problem where I have 2 classes, positive and negative. Okay, so far in this course, we have seen accuracy, which is basically the number of correctly classified instances right, divided by total number of instances. Total number of instances, right? So now, is this a good metric? Is this a good metric for all tasks? Okay, so let's consider an example task. Okay, so we are going to consider the problem of cancer prediction. So given a patient record, we are interested in predicting whether the patient has cancer or not. Okay, so let's say we have 10,000 patient records. Cancer is not a very rare, it's not a very common disease. So like probably 9,900 patients record says cancer is equal to no. Okay, and 100 patients record says cancer is equal to yes. Okay, so there are 100 cancer patients and 9,900 patients who do not who does not have cancer. Okay, so now let's consider a very simple classifier. Okay, now this classifier is going to take the patient record. Okay, and there is nothing inside this classifier. So this is just going to predict always no. Okay, now what is the accuracy of this classifier in this training data? Maybe answers in chat. So what would be the accuracy of this classifier, which says always no? Okay, so it's 99%, right? So this classifier has accuracy 99%. Okay, now the question is this a good classifier? It has 99% accuracy. Is this a good classifier? No, clearly not, right? So like this is such a useless classifier. This is useless classifier because it is not predicting any cancer patients, right? Like, so on the other hand, the only reason why we go for such a prediction model is to figure out who has cancer, right? Like, so now this tells us something. So this tells us that not every error has same cost. Okay, so at least in this cancer prediction problem, there are two types of error. So the first type of error is when you classify patients without cancer to S. So this is wrong because the patient does not have cancer, but you're saying, yes, the patient has cancer. Similarly, like there's another type of error, which is classify patients with cancer to no. Okay, so maybe let's try a poll. So which one of these two errors is like more dangerous? Okay, so I'm going to do a template poll. A for first type of error, B for second type of error. Okay. Okay, so I will stop the poll. You have to be fast in polling. Okay, so I'm stopping the poll. So I see that 75% of you think it is 2. But actually, like in fact, it is the second one, right? Like the second one is more dangerous than the first one because sometimes it is actually okay to say someone who does not have cancer it's okay to classify them as yes, because in the first type of error, like the patient might actually go do a couple of more tests, and then better tests would tell that the patient does not have cancer. Yes, it is true that there is some some stress that is given to the patient because of this wrong classification. But that stress is actually better than the second situation where someone has cancer and your system says they do not have cancer and they go back home and the cancer progresses and their life is in danger, right? So the second type of error is more dangerous than the first type. Okay, so now is there a way to weigh different types of errors based on the importance of like the error, right? Like so there is one way in which you could do this, which is the idea of confusion matrix. Okay, so the confusion matrix is going to separate these different types of errors so that you can treat them separately. Okay, so now remember we are in the situation of positive and negative classes, right? So now I'm going to construct this 2x2 matrix where this is the true value, okay, and this is the model's prediction. And there is true positive values, negative values. Similarly, the model's prediction of positive and negative. Okay, so now if you look at the first box, this is when the example is true, like it's truly, the example is positive and the model is also saying it is positive. So it's a correct classification, right? So this is true positive. Okay, similarly, this box is when the example is negative and the model is also saying it is negative. So this is true negative. Okay, so now let's look at this box. What does this mean? The blue box means the example is negative, but your model is saying that it is positive. Okay, your model is falsely classifying these examples as positive. So we're going to call this as false positive. The easy way to remember this is it's falsely positive. Okay, similarly, this box is falsely negative. So it's false negative. Okay, so now let's go back to this. Okay, another poll. So look at the first type of error. Classify patients without cancers as yes. Okay, so like what type of false like false prediction is this? Is it false positive or false negative? So maybe, well, I cannot put both in the same slide. So classify patients without cancer as yes, right? Like, so is this false positive or false negative? So let's do a poll, A for false positive, B for false negative. A for false positive and B for false negative. Okay, so let's stop the poll. Well, most of you agree that this is false positive, right? So in this case, it's easy to say because the model is having a positive classification, but it is not positive. It's supposed to be negative. So the type 1 is false positive and type 2 is similarly false negative. Okay. Okay, so now this is the idea of confusion matrix. So now let's consider an example problem. Okay, so I have 100 examples and 60 of them are positive and 40 of them are negative. Okay, so now if I look at an example confusion matrix, true, positive, negative, positive, negative, this is model's prediction, right? So let's say I have something like this. So here you can see that there are 40 examples which are actually positive and the model also classified it positive, right? Similarly, there are 30 examples which are actually negative and the model also classified it as negative. Now, these two are the errors that the model is making, right? So now if you sum up the first column, you should get all the positive examples, 60. Similarly, if you sum up the second column, you should get all the negative examples, which is 40, okay? Now, this is the property of this confusion matrix. Okay, so now can someone tell me what would be an ideal confusion matrix? So maybe hand raise or chat. Okay, so it's a diagonal matrix, right? Like an ideal confusion matrix for, sorry, this example is actually 60, 0, 0, 40, right? So this is ideal because this classifier had no error. 60 positive correctly classified as positive, 60, 40 negative correctly classified as like negative, right? Now here is an example of a very bad confusion matrix. Like, so if you have something like 30, 30, 40, 30. right? So this is an example of a bad confusion matrix. Why? Because this model is confusing a lot between these two classes. It's like 30-30 for positive and negative, right? Almost 50-50. This is an example of a random classifier. So by just looking at the confusion matrix, you can say a lot about how random is this classifier. And in fact, if you have a confusion matrix for 5 classes, like it's going to be a 5 class 5 matrix, right? So then you can say, for example, by just looking at the confusion matrix, you could say, oh, this model is confusing class 1 with class 3. So maybe they are very similar classes. Okay, so these kind of qualitative analysis can be easily done by just looking at the confusion matrix. Okay, now that we have developed this idea of confusion matrix, so we are going to use this confusion matrix to come up with better metrics than accuracy. Okay, so sorry, let me just copy paste the confusion matrix to the next page. Okay, so now using this confusion matrix, we are going to define 2 new metrics. Okay, so the first metric that I'm going to define is precision, which is basically true positive divided by true positive plus false positive. Okay, similarly, I'm going to define another metric, recall. So I will intuitively explain what is precision and recall, but first let's define them. So recall is given by true positive divided by true positive plus false negative. Okay, so now what is true positive plus false positive? So it is, let me try to use a different color. What is true positive plus false positive? It is basically this entry, right? So this row, the first row is basically all the positive predictions that this model has made. So in the cancer example, the denominator is the sum, denominator is basically the total number of cancer patients that the model identified, okay? And the numerator tells us how many of them actually had cancer, okay? So in some sense, like an English description of precision or literal, like is out of all positive predictions that my model made, okay, how many of them are truly positive? If my model makes 100 positive, 100, if a model says there are 100 patients who have cancer, how many of them truly have cancer? Okay, that is precision. Now let's look at recall. So recall is a different type of metric. So what is the denominator in recall? It is basically TP plus FN, right? So let me see if I can find another color. So like this orange is the denominator in recall, right? So what does this mean? This is actually all the original true, like original positive examples. So recall tells you how many of these total number of real positive examples your model can recover. Okay, so again, like the English description of recall, out of all positive examples in the data, see the change in the change in the focus. So in the case of precision, it is out of all positive predictions by the model. But in the case of recall, out of all positive examples in the data, how many of them are correctly identified as positive by the classifier? Okay, so now that I have explained what is precision and recall, so can someone tell me which is a better metric for the cancer prediction problem? So is it precision or recall? Maybe chat. Okay, so all of you agree, well, not all of you agree it is recall. Some of you still think it is precision. Some of you think it might be a combination. Okay, let's not think about the combination right now. I'm giving you only 2 options. You could have good precision or you could have good recall. So let's not jump to the next topic. So you can have good precision or good recall. That is the trade-off that I'm giving you. Which one would you choose? So it's, well, most of you agree that it is recall, right? So you don't want to miss someone who has cancer by saying he doesn't have cancer. So if there's any cancer patient in the data, you want to predict them correctly at the cost of falsely predicting someone to have cancer even though he doesn't have. Okay, so if I give you only the option of precision and recall, it is going to be recall. But there are many situations where precision is more important, and there are many situations where recall is more important. Okay, I will give this as an exercise for you, like to go think about what are the applications where precision is more important and recall is more important. So I would just list a couple of them. So, okay, so in the case of, like, to give you an example for situations where precision is more important, so one application that I could think of is face password systems. Now with new iPhones, you have face detection based passwords, right? So now in this case, I want a system which is highly precise, like more precise than like more recall. Like why? Because I don't want my phone to be accidentally opened by someone else just because my model thought it is me, right? On the other hand, probably I'm okay if my models, like, let's say I shave one day, or I did not shave one day. Like, let's say the model says, oh, like you are not Sarath, like, so I'm not going to open. It is okay. In that case, I could actually use my like PIN password, like, or number password to enter, right? So in this case, we don't care about the recall. Like, we care more about being precise. Like, we don't want a wrong person, one wrong person to enter my like my phone because of the mistake that the face password system is doing. To give another example for recall, like we have already seen cancer, to give another example for recall is the email spam classifier, right? So we are usually kind of okay if a spam gets into our original, like the good email box, but we are not okay if the good email goes to spam accidentally, right? Let's say you have a very important email and it goes to spam. That is not acceptable. In this case, you want recall of original emails, like the good emails, okay? Okay, so, but why do we have this trade-off, right? So why focus on just precision or just recall, right? Like, it's because actually it is easy to achieve high precision at the cost of low recall, and vice versa. Okay, I can give you the best example classifiers for this. Okay, so let's say I have a classifier which by default always says yes. Okay, now this classifier would have 100% recall, but very bad precision, right? Similarly, if I have a classifier which always says no, then this is going to have 100% precision, right? So it's ironic because it never said yes. So whenever it says yes, it is precise, right? So it's 100% precision, but very bad recall. Okay, so there is always this way to cheat and get high recall at the cost of low precision. Okay, now in reality, in most of the applications that we care about, we would want both precision and recall. What if both precision and recall are important? Okay, so for example, in the case of cancer prediction, I was being an extremist and said, okay, so I just care about recall, not precision, right? Like, but if you are running a famous hospital, like, you would also care about the precision. Like, you don't want people to think that, oh, if you go to this hospital, they would always give you false notification that you have cancer, but you don't have cancer. Okay, so now, like, also, like, it could have both types of effects. Like, for example, like if you are putting the patient through a lot of mental stress, because like if you're putting a lot of your patients in mental stress because every time someone comes you say he has cancer, that is also not good, right? Like, so in reality, for cancer prediction, you actually need both good precision and recall. Okay, so now there is another metric which captures both precision and recall, and it is known as F1 measure. Okay, so F1 measure is simply the harmonic mean of precision and recall. So it's basically 2PR by P plus R, where P is the precision and R is the recall. Okay, now this is just the harmonic mean of precision and recall. Okay, so if you have high precision and high recall, F1 measure is going to be high. Similarly, like if your F1 measure is high, it means you have both high precision and high recall. Okay, so now this is very difficult metric to like satisfy when compared to just precision and recall. And I think in your assignment 2, you will be using all these metrics. Okay, so well, there are actually many other metrics for classification. Like, so there is, for example, area under the curve, ROC, and like there is there's precision recall curve. Okay, like we are not going to cover in detail like different other classification like the ones that we have seen are the most common. So I will leave it to you as a reading probably for the next week about different other metrics for evaluation. And also as a part of next week reading, you will read about how to extend these to multi-class problems. Okay, I think that is a short discussion about evaluation metrics before we move to the next part of the lecture. Is there any questions? This is the time for you to raise your hands. Any questions? Is it possible to have both precision and recall above 50%? Yes, of course. You can have models which are highly precise and highly and has high recall. But they are difficult to achieve, but you can do it but it's not impossible. Any other questions? Okay, so maybe we will continue. So, okay, so far, like our discussions about classification algorithms were mostly based on probabilistic generative models. Now we are going to see another class of like classification algorithms, which is probabilistic discriminative models. Okay, so remember that in the case of generative modeling, if you had a two-class problem, then you had the sigmoid formulation where probability of C1 given X is given by sigma of W transpose X plus W0, right? And in the case of like multi-class problem, you had probability of the class vector like given X is given by softmax of W transpose X plus W0, right? So this is for two class and this is for K class, right? And we actually had a detailed equation for what is W, what is W0, right? Like so these W and W0 were basically functions of mean, variance, and prior probabilities, right? Okay, so if you remember the two assumptions with which we started generative modeling, the first assumption was the class conditional densities are Gaussian. And the second assumption was the fact that the Gaussian shared the covariance matrix, but we have already like relaxed the second assumption in the previous lecture. So we can actually we even have algorithms like QDA where like the class like covariance matrix, the class individual class covariance matrices are not shared, right? Like, but throughout like our discussion, like we still had the first assumption, which is probability of CK given X is Gaussian, right? So here is the problem. So as I said before, for most of the real life, well, Gaussian is a very decent approximation because like of several nice properties of the Gaussian distribution and law of large numbers, right? But there are many applications where oh, sorry. Yeah, it's X given CK. Someone is listening. X given CK. Okay, so okay, so Gaussian is a decent assumption, but like it is not going to be true in many in many applications, okay? Also, the moment you start changing your assumption to some other distribution, you have to do the entire derivation again to come up with W and W0, right? So this is going to be a tedious process, right? Like, so every time you want to come up with a generative model, like you need to make an assumption about the distribution, and then for that particular assumption, like you're going to come up with for that assumption, you're going to come up with like the whole derivation of W and W0, right? So instead of going through this complex process, the discriminative approach gives us a very simple solution. Okay, so the discriminative approach, as we know from the definition, is just focusing on the probability of C1 or Ck given X, right? It just cares about the probability. It doesn't care about not about probability of X given Ck or P of Ck, right? So this is generative models. On the other hand, discriminative approaches would just care about probability of Ck given X. So the idea here is, instead of having a separate formulation for W and W0, why don't we just treat W and W0 as just our parameters and directly learn W and W0 by using gradient descent, okay? So now W is not an equation of mean, variance, or prior. W is just like a vector parameter. So now I have W and W0, just like how we had these parameters in linear regression, right? And I'm going to learn them directly by using maximum likelihood. Okay, so that is the discriminative approach. Basically, you assume W0 as a vector of parameters and learn them directly by using maximum likelihood. Okay, so now what are the advantages of this model? The first advantage is the fact that there are actually, the moment you say that W is my parameter, I don't care about mean, variance, and prior, you are saving a lot of parameters, because remember that you needed n times k times m parameter for mean, k times m square parameter for variance, and so on, right? So you needed a lot of parameters in this generative model. In this case, there is basically fewer number of parameters than the generative approach. Okay. Similarly, you would actually get improved performance if the class conditional density assumptions of generative models are wrong. Okay. If the class conditional density assumption of GDA is wrong or poor approximation, let's say it's a poor approximation, then discriminative model will perform better. Okay. Okay. So now this idea of taking this sigmoid formulation or softmax formulation and just throw away all the assumption and directly learn W and W0, right? So now this is known as logistic regression. Okay. So logistic regression is a very simple model. Probability, let's just focus on the 1-2 class setting. Probability of C1 given X is given by Y of X, where Y is my function, which is sigma of W transpose X. Okay. For just to make things easier, like I'm not adding a bias here. Like, so bias goes inside the W if you add one, like if you append 1 to X. Okay. So let's just call this as W transpose X. Okay. Now probability of C2 given X is given by 1 minus probability of C1 given X. Simple, right? So this is known as logistic regression, but remember that this is used for classification. The name is a bit confusing. It's called logistic regression because it looks very much like regression except for the logistic sigmoid function, right? So, but it is a classifier. Okay. So now how many parameters do you need for logistic regression? Let's say I have m features. Okay. Can someone tell me in chat how many parameters do I need for this model. Let's see. M plus 1, right? So if you have M features, you need M parameters for the features plus 1 bias. So this model only requires M plus 1 parameters. On the other hand, models like GDA is going to require way more parameter. Okay. So now let's see how to learn these parameters for logistic regression. Okay. So we are going to do the usual thing that we do for probabilistic models, which is the idea of maximum likelihood for logistic regression. Okay. So now let's consider a data set which has a bunch of examples, Xn and Tn. Okay, where Tn belongs to 0 or 1. Okay, so remember that in the case of generative model, we were interested in maximizing the likelihood of the entire data, right? So in the case of generative model, we were interested in maximizing the probability of X comma T, right? But in the case of discriminative model, which is logistic regression, we would just care about like maximizing the probability of T given W. Okay, which means we need to know what is P given W, P of T given W. So P of T given W, again, we are going to make the IID assumption, which means the probability of the entire data set is given by product of the individual probabilities. So product over n examples. Okay, now I'm going to write the formulation directly here, but we have done this previously. Okay, so for T of n is equal to 1, for class 1, the probability is given by, you can see here. For class 1, the probability is given by y, right? So for class 2, the probability is given by 1 minus y, right? So I'm going to directly write the likelihood. So it is y if the class is 1. It is 1 minus y if the class is 0. Okay, so we have done this before, like I'm just directly writing it this time, where T is basically the vector of all the targets. Okay, and similarly, like what is y of n? Y of n is basically probability of C1 given Xn. Is that clear? Okay, now we want to maximize this function. Okay, so let me maybe cut this function and move it to the next page. Copy. Okay. Okay, I copied a lot of other things. Okay, so now this is the function I want to maximize. Okay, so now it so happens that for this particular function, there is no closed form solution. So when you don't have closed form solution, we know what to do, right? Like, so we would go for gradient descent. Okay, so, well, technically gradient descent is finding the minimum, right? In this case, you want to find the maximum, right? So you want to maximize the log likelihood, so likelihood or log likelihood if you want to, right? So just to bring it back to our usual gradient descent formulation, we are going to define our own error function, which the gradient descent can minimize. The error function is simply the negative of the likelihood. So if you're minimizing the error function, which is the negative of the likelihood, then you're implicitly maximizing the likelihood, right? So the error function is given by negative log likelihood. We will shift to log because it's easy to deal with. Okay, so now the error function is defined as minus ln probability of T given W. Okay, now the moment you put log to this whole error function, like the product becomes summation, right? So it becomes summation over n is equal to 1 to n. It's minus of this term, so minus, okay, you do the ln. So you do the ln for this, the exponents will come to the left, right? So this becomes t power n ln y of n plus 1 minus t power n ln 1 minus y of n. Clear? Okay, where y of n is given by sigma of some a of n. Okay, the a of n is the W transpose x. Okay, so we're going to call this input that you're giving to the sigmoid as activation. Like, let's say pre-activation. Okay, so you have this pre-activation A, which is simply W transpose X. You pass it through the sigmoid, and then you get the Y. Okay, now depending on the Y, you compute the error function. Okay, so now we want to do gradient descent here. So which means we need to find dou E by dou W, right? Okay, so now this is where we are going to use your basic calculus. So I'm interested in deriving, differentiating W with respect, E with respect to W, okay? Do you see E, like W in this equation? No, you don't see W in this equation. You only see Y, okay? So now we can apply chain rule so that we first differentiate this term with respect to Y and go to Y, and you see that Y is actually a function of A, right? Again, you have to go back in your chain, and A is the function of W. So now I can represent this dou E by dou W as summation over n is equal to 1 to n, okay? Dou E by dou Yn by dou An by dou W. Okay, so this is just the basic chain rule, because we have this model which is a function, right? So error is the function of y is the function of activation is the function of W. Okay, so now this, let's just call this one. Okay, now we just need to compute these three terms. Okay, so it's very simple. So let's start with dou E by dou Ym. So what happens if you differentiate? Okay, so remember we are just doing for one example. So you just consider this term. You differentiate this orange term with respect to y. So you would have, so there is a minus in the front, remember that. So it's minus t of n by y of n. When you differentiate ln y, you get y, like 1 by y, right? And you get minus 1 minus t of n divided by 1 minus y of n. You differentiate 1 minus y of n, so you get a minus, so it becomes plus. Okay, so now I could actually simplify this, but let me take this to the next page to simplify. Copy, paste. Okay, so we could easily simplify this. So this becomes 1 minus t of n times y of n. This is the second term, right? Minus t of n times 1 minus y of n, which is the first term, divided by y of n times 1 minus y of n. And I just expand this. So this becomes y of n minus t of n y of n minus t of n minus t of n y of n. Sorry, plus, okay, divided by y of n 1 minus y of n. So now these terms cancel, right? So this becomes y of n, okay, minus t of n divided by y of n times 1 minus y of n. So now this is dou E by dou Yn. Let's call this as equation 2. Okay, now what is the next differentiation we want? We want to differentiate dou Yn by dou An. So let me write the Yn function here for easiness. Okay, so y of n is given by sigma of A of n. Remember? So we have, so basically we need to do dou by dou An of sigma of A of n. So if you remember my note from the time when I introduced sigmoid function, the differentiation of sigmoid is basically sigma times 1 minus sigma. So this becomes sigma of A of n times 1 minus sigma times A of n. Okay, so let's just call this as equation, well, like, see, what is sigma of A of n? It is y of n, right? So this is basically y of n times 1 minus y of n. So this is dou Yn by dou An. Okay, so let's just call this as equation 3. Okay, so far we have computed the first part of the chain rule, the second part of the chain rule. The third part of the chain rule is really easy, which is dou an divided by dou w, the final part, right? So now again, to remember, a of n is given by w transpose x. So when you differentiate w transpose x with respect to w, you get x. Let's just call this as 4. Okay, so now we have all the three terms. We are just going to substitute these three terms to this particular chain rule. Okay, so maybe let's cut this chain rule and move it here. Okay, so now we have this chain rule, and this essentially becomes summation over n is equal to 1 to n. The first term that we derived is y of n minus t of n divided by y of n times 1 minus y of n. Okay, and the second term that we derived is y of n times 1 minus y of n. Okay, and the third term that we derived is x of n. Okay, you can see that this cancels. So we ended up with summation over n is equal to 1 to n, y of n minus t of n multiplied by x of n. Okay, now this is my gradient. Do you remember this formulation like from the previous lectures? Like, so have we seen something like this before? Y of n minus t of n times x of n. Any hand raised, chat? So have we seen something like this, some gradient like this before? Okay, so linear regression, right? Like, so this is same as linear regression, right? Like, so basically, if you remember, the stochastic gradient doesn't update for linear regression. Like for the W part, it is exactly y minus t times x of n, right? So, well, I wish I could finish the connection, but maybe let's just leave the connection as a puzzle for people who haven't read the notes yet. But if you have read the notes, you know the answer. But here's the connection, right? Like, so, like, remember that in the case of logistic regression, we are using negative log likelihood error function. Okay, but in the case of linear regression, we were using least square error function. Okay, but it so happens that in both these situations, the gradient looks exactly same. Okay, now this is not a coincidence. There is actually a deep connection between maximum likelihood and least squares, but still we are running out of time. We are going to see the connection after the break, like after the study week. Okay, but I think like we have, so as far as logistic regression is considered, we have covered the model. Like, so we know the model, we know how to come up with gradient descent for finding the parameters, right? Like, so this concludes the discussion about the classifier itself. But we will spend more time on like trying to connect between these two types of error functions in the next lecture. So I think I could take some questions now. Okay, a quick reminder. So next week is study break. So there are no lectures, but there will be office hours. So you could use office hours to talk to, like I will do my office hours in the same link, but you could also use office hours of other TAs during the week. Try to finish your assignment 1 tonight. You have 3 days of late with penalty, but like try to do it tonight and like focus on probably, okay, like we don't have a midterm for the course. I know that you might have midterm for other courses, but for the study week, I would actually recommend you to go through all the lecture notes once, and I will try to upload the self-assessments and scribbles for every lecture, like by today or tomorrow, so that all the material that you need is there. But I would highly encourage you to go through all the lecture notes, master the material, because as you see, we are slowly ramping up in terms of speed. So like as we see more and more like new algorithms, we are going to connect these algorithms and start talking at a much higher level. So like it is very important, like so far, whatever we have seen in this course are the fundamentals and like very basic things. and you should definitely master these things and like make sure that you know every bit of it. Okay, so maybe I will take a couple of questions before I stop the recording. Any questions? Okay, so Remy, you can leave. Thank you. I'm going to let people unmute themselves.
Hello, I have a question.
Yeah.
So, since it's the first time you're giving the class, we don't have access to previous exams, so like a practice final. Could we
That is
have
why we
one?
have self-assessment questions.
Okay, so we can assume that the exam is similar.
Not similar, but like, okay, here's the thing. If you can answer all the self-assessment questions, then you could answer everything in the exam.
Okay.
I think self-assessment questions are probably way more dense than giving previous exams. So please make use of it. Okay, any more questions? Look, I'm going to stop the recording, but I would still stay for a few minutes if you have any questions.